Welcome to this comprehensive guide on behavioral design patterns in Go programming language. Behavioral patterns are a fundamental category of design patterns that focus on communication between objects and the distribution of responsibilities. In this tutorial, we will explore three essential behavioral patterns: the observer pattern, the strategy pattern, and the command pattern. These patterns leverage Go's unique language features such as interfaces, channels, and Go routines to create elegant and efficient solutions. Each pattern addresses specific scenarios in software development, helping you write more maintainable and flexible code. Behavioral patterns are design patterns that focus on algorithms and the assignment of responsibilities between objects. Unlike creational patterns that deal with object creation, or structural patterns that deal with object composition, behavioral patterns are concerned with how objects interact and communicate with each other. These patterns define the communication protocols between objects and help manage complex control flow in your applications. The two key areas that behavioral patterns address are communication and responsibility distribution. Communication involves defining how objects interact and communicate with each other effectively, ensuring that messages flow smoothly throughout your system. Responsibility distribution focuses on distributing responsibilities among objects to manage complex control flow, making sure that each object has a clear and well-defined role in the overall system architecture. The observer pattern is a fundamental behavioral design pattern that defines a one-to-many dependency between objects. When one object changes state, all its dependents are automatically notified and updated. This pattern is particularly useful in scenarios where you need to maintain consistency between related objects without tightly coupling them together. The observer pattern excels in two main use cases. First, it's perfect for event systems where you need to notify multiple subscribers when events occur in your system. This could be anything from user interface events to system-level notifications. Second, it's ideal for state changes where you need to keep multiple objects synchronized with state updates. This ensures that when the state of one object changes, all dependent objects are automatically informed and can react accordingly. Implementing the observer pattern in Go leverages the power of interfaces to create a clean and flexible design. The pattern consists of two main interfaces: the observer interface and the subject interface. The observer interface defines a single method called notify that takes an event parameter. This method is called whenever the subject needs to inform the observer about a change. The subject interface defines three essential methods: register for adding new observers, unregister for removing observers, and notify all for sending notifications to all registered observers. This interface-based approach in Go provides excellent flexibility, allowing any type that implements these interfaces to participate in the observer pattern without inheritance hierarchies. Let's examine a practical example of the observer pattern using a news publishing system. The publisher struct represents the subject that maintains a list of observers and stores news content. It includes an observers slice to keep track of all registered observers and a news string to store the current news. The publish method updates the news content and then calls notify all to inform all observers about the new news. On the observer side, we have a subscriber struct that represents entities interested in receiving news updates. Each subscriber has a name for identification. The notify method implementation prints the received news to the console. But in real applications, this could trigger more complex behaviors like updating user interfaces, sending emails, or logging events. This example demonstrates how Go's interfaces make the observer pattern both simple and powerful. A strategy pattern is another essential behavioral design pattern that defines a family of algorithms, encapsulates each one, and makes them interchangeable at runtime. This pattern is particularly powerful because it allows you to change the behavior of an object dynamically without modifying its structure. The strategy pattern shines in two primary scenarios. First, it's excellent for algorithm switching. where you need to choose different algorithms based on context or user preferences. This could include different sorting algorithms, compression methods, or calculation strategies. Second, it's perfect for behavior variation, allowing you to vary an object's behavior without changing its class structure. This promotes flexibility and maintainability by separating the algorithm implementation from the client code that uses it. The strategy pattern implementation in Go follows a clean interface-based design that takes advantage of Go's powerful interface system. The core of the pattern consists of the strategy interface, which defines a single execute method. This method takes data of interface type and returns interface type, providing maximum flexibility for different strategy implementations. The context structure holds a reference to the current strategy and provides methods to work with it. The context struct contains a strategy field of strategy interface type, and the setStrategy method allows changing the strategy at runtime. This design enables the context to delegate algorithm execution to the current strategy while remaining completely independent of the specific algorithm implementation. The flexibility of Go's interface system makes this pattern particularly elegant and easy to implement. Here's a practical example of the strategy pattern implemented for a payment processing system. We define different payment strategies, such as credit card and PayPal, each implementing the payment strategy interface. The credit card struct implements the execute method to process payments via credit card, displaying the payment amount and method. Similarly, other payment methods, like PayPal, would have their own implementations. The payment context struct serves as the context that holds the current payment strategy. It includes a strategy field and a pay method that delegates the actual payment processing to the current strategy. This design allows the application to switch between different payment methods dynamically without changing the core payment processing logic. The beauty of this approach is that adding new payment methods requires only implementing the payment strategy interface, making the system highly extensible. The command pattern is a behavioral design pattern that encapsulates a request as an object, allowing you to parameterize clients with different requests and queue operations. This pattern transforms requests into standalone objects that contain all information about the request, enabling powerful capabilities like undo operations, queuing, and logging. The command pattern excels in two key areas. First, it's perfect for implementing undo and redo functionality by storing commands in a history stack. Each command object knows how to execute and reverse its operation, making it possible to build sophisticated undo systems. Second, it's excellent for queuing operations for batch processing or delayed execution. Commands can be stored, transmitted, and executed at different times, making it ideal for scenarios like job scheduling, macro recording, or implementing transactional behavior in your applications. The command pattern implementation in Go centers around two main components: the command interface and the invoker structure. The command interface defines two essential methods, execute and undo. The execute method performs the actual operation, while the undo method reverses the operation if possible. This dual method approach enables powerful undo and redo capabilities. The invoker structure manages command execution and maintains a history of executed commands. It contains a history slice that stores all executed commands, providing a complete audit trail. The execute method of the invoker takes a command, executes it immediately, and then appends it to the history. This design allows the invoker to track all operations and potentially implement complex undo and redo mechanisms by traversing the command history. Let's explore a practical implementation of the command pattern using a text editor example. The write command struct encapsulates a text writing operation, containing references to both the text editor and the specific text to be written. The execute method calls the write method on the editor with the specified text, while the undo method could implement text removal logic. In the main function, we demonstrate how to use the command pattern by creating a text editor instance and a write command with the text hello. The invoker executes the command, which writes the text to the editor and stores the command in history. Later, we can call the undo method on the invoker to reverse the last command. This pattern is particularly powerful in applications like text editors, graphics programs, or any system where users expect undo and redo functionality. Let's summarize the key concepts we've explored in this comprehensive guide to behavioral design patterns in Go. The observer pattern enables one-to-many notifications using Go's interfaces and channels, making it perfect for event-driven architectures and maintaining object synchronization. The strategy pattern provides interchangeable algorithms through Go's interface composition, allowing dynamic behavior changes without modifying existing code structure. The command pattern offers request encapsulation that enables powerful undo and redo functionality, making it ideal for applications requiring operation history and reversibility. Go's unique advantages make these behavioral patterns particularly elegant and effective. The combination of interfaces, Go routines, and channels in Go provides a powerful foundation for implementing these patterns in a more concurrent and efficient manner than traditional object-oriented languages. These patterns leverage Go's strengths to create robust, maintainable, and scalable applications that can handle complex behavioral requirements with simplicity and clarity.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.